We have driven rovers across Mars, dropped a probe into the clouds of Saturn, photographed Pluto up close. Crossing billions of kilometers has started to feel ordinary. One direction has not. Straight up, out of the flat plane the planets share, directly above and below the Sun's poles. It should be the easiest place in the solar system to reach. It turns out to be harder than going to Pluto. For almost all of human history, no eye had ever seen what waits there, or looked down on our own home from above. And the way out begins with the strangest move of all. A probe that must first fall toward the Sun before it can climb. When we say above or below the solar system, above or below what exactly? In space, there is no floor. There is no ceiling. There is no single direction everyone in the universe has to agree is up. Two astronauts can drift face to face. One of them turned completely over compared to the other, and neither one is upside down. Both are just floating. Up and down, out here, are not laws. They are agreements. So we need to be honest about what the agreement is. The planets all circle the Sun inside a thin, flat sheet, the way runners stay on a track. Astronomers call that sheet the ecliptic. It exists because the solar system was born from a spinning cloud of gas and dust. As that cloud collapsed under its own gravity, it spun faster and flattened out. A figure skater pulling in her arms speeds up the same way. So does pizza dough when you spin it into a disc. Four and a half billion years later, the planets are still riding that frozen sheet. The sheet is not perfectly clean. Most of the major planets sit within about 7 degrees of it. Pluto, the dwarf, leans nearer to 17 degrees, and some comets fall in from almost any angle, like needles through a spinning record. But the big worlds hold close to the flat. So above or below the solar system means one thing: the two directions that point straight out of that sheet, toward the empty space over the Sun's North Pole and under its south. Up is not a place the universe marked for us. It is just the way off the disk. So if up out of the solar system only means straight off this flat sheet, why has almost no spacecraft ever gone there? The answer is not distance. The answer is speed, and you are carrying it right now. The chair you are sitting in is moving around the Sun at roughly 30 kilometers every second. That is about 67,000 miles per hour. In the time it takes to listen to this sentence, you and the ground under your feet have slid more than 100 kilometers sideways. You have felt nothing at all. Everything around you is racing on the same flat track. Every planet, every moon, every rocket we have ever launched, welded to one racetrack none of us can feel. That inherited speed is a gift in one direction. It is a wall in every other. To send a probe to Mars, you only need to change your speed by about 4 kilometers per second. because Mars is already moving the same way you are. You are nudging forward along the track, but to go straight up, that 30 kilometers per second of sideways motion becomes your enemy. You cannot use any of it. First, you have to cancel almost all of it. Erase the speed you were born with. Fight 4.5 billion years of momentum, and only then begin to climb. That is nearly 10 times the cost of reaching Mars. To feel the size of it, 30 kilometers a second would carry you from New York to Los Angeles in about 2.5 minutes. That is the speed you would have to throw away just to hang still above the sun. Here's where it stops feeling like math. Pluto sits about 3.5 billion miles out, roughly 5.5 billion kilometers at the frozen edge of everything we know. Reaching Pluto takes less energy than reaching a point a few million miles straight above the sun's north pole. The far edge of the solar system is easier to touch than the air right over our own star. We are not walled in by distance. We are walled in by our own speed. That is why no rocket just points up and goes. Burning enough fuel to cancel out 30 kilometers per second is a fantasy. So every serious design has to steal motion from a planet's gravity instead of fighting it. Because climbing out is so expensive, almost nothing has ever gone there. Which is why the space above the sun is still a blank spot on our maps, even now. We have been picturing up as if our flat sheet were lying neatly along the floor of the galaxy. It is not. The plane of the solar system is tilted to the plane of the Milky Way by about 60 degrees, close to 60.2, if you want one firm number instead of a vague gesture. We do not ride level through the galaxy. We ride at a steep slant. That slant changes what up even means. The whole solar system is sweeping around the center of the galaxy, dragging every planet with it. So the direction we call above and below the sun is, in a real sense, closer to ahead and behind us as we travel. The space over the sun's pole is partly the road we are driving toward. We are not a still pond. We are a current. And the current is fast. The sun carries us around the galactic core at about 230 kilometers per second, a little over 800,000 kilometers per hour. One full lap takes somewhere near 225 million years. One galactic year. The last time the solar system sat exactly where it sits tonight, dinosaurs were the most advanced thing walking the Earth. So our true path is not a flat circle at all. It is a long, slow spiral through the galaxy, and what counts as up keeps quietly turning with it. As for what actually lies out that way, the icy edge of the Oort cloud, then other stars, then the rest of the galaxy, that is a story for another night. This one stays close to home. Because the real question is not only what is up there, it is whether we have ever managed to look. And for one place in particular, the sun's own poles, the honest answer, until very recently, was no. Look straight up from the sun, and you are staring at its poles, the top and bottom of our own star. They may be the most important ground in the solar system. The fastest solar wind pours out from there. The sun's magnetic field turns itself completely inside out every 11 years, north becoming south, and that violent flip begins at the poles. Yet for the whole of human history, we have only ever watched the sun from the side. It is like trying to learn the weather of an entire planet while standing forever at its equator, never once allowed to walk to the pole. We tried to change that decades ago. A spacecraft named Ulysses, launched in 1990 by NASA and the European Space Agency, became the first machine to fly over the sun's poles. But it could not turn upward on its own. It had to fly all the way out to Jupiter in early 1992, let the giant planet's gravity fling it nearly 80 degrees out of the plane. It worked. Ulysses sailed over both poles 3 separate times across more than 18 years of life. Up there, it found the polar wind blowing steady at around 750 kilometers per second, nearly twice the speed of the slower wind near the equator. It felt the poles in detail no one had before. It carried no camera that could photograph them. Think of every blank space humans have ever drawn on a map. The edges where old cartographers wrote here be dragons, the white interiors of unmapped continents. One by one, someone walked into each of them. This was the one blank we could measure but never picture. A frontier we charted with magnetometers and particle counters, feeling its shape in numbers while it stayed, to our eyes, completely dark. For 35 years, that was the closest we ever came. Measurements without a single photograph. Then last year, that changed. By 2025, the European Space Agency's solar orbiter had spent years quietly bending its path. Each close pass of Venus tipped its orbit a little further out of the flat plane, trading speed for angle, climbing slowly toward a view no spacecraft had ever held. In the middle of March, it tilted far enough, about 15 degrees below the sun's equator, then 17, to look down at the sun's south pole and send the pictures home. They were the first images of a pole of our star in the history of our species. It is worth saying plainly who confirmed that, because this is the kind of claim that deserves a name attached. Today we reveal humankind's first ever views of the sun's pole, said Carol Mundell, the agency's director of science. Every photograph of the sun taken before that moment, every one across all of history, was shot from somewhere near the equator. The Earth and every telescope we had ever flown were trapped in the same flat plane as the planets. We had been looking at our own star edge on for as long as we had been looking at all. And the face it finally turned toward us did not look calm. Instead of the smooth, ordered bands we know from the side, the South Pole showed a chaotic, tangled knot of magnetism. North and South polarities jumbled together in the same place at once. It was the fingerprint of a star near the peak of its cycle, gathering itself to flip. The full set of pole-to-pole data only finished arriving later in the year. For decades we had described the roof of our own house from the ground, guessing at it. In March of 2025, for the first time, we climbed high enough to see it. And the roof was on fire in a pattern no model had drawn. Seeing the pole was only half the prize. There is something even larger we have never seen from outside, and we are sitting inside it right now. Around the Sun, there is an enormous invisible bubble called the heliosphere. It is the solar wind blown outward in every direction, pushing back against the thin gas between the stars. Everything you have ever known sits inside it. Every planet, every comet, every probe. For a long time, the textbooks drew that bubble like a comet. A round head facing the way we travel, and a long tail trailing behind. It looked right. It was almost certainly wrong. In 2020, a team led by Merav Ofer at Boston University ran a fresh model on NASA data and got a different shape. Charged particles picked up at the edge of the bubble seemed to leak away too quickly to form any long tail. In their leading version, the heliosphere looks less like a comet and more like a deflated croissant. A curved, puffed center with two jets curling off the sides and no tail. Other teams still argue for the tail. The real shape is genuinely unsettled, and that is the whole point. We have never once looked at the bubble from outside. Every picture we have is built from models and from particles counted from within. A common correction belongs here, and viewers are right to raise it. The two Voyager probes did cross the edge of the bubble in 2012 and 2018. That part is real. But they crossed it sideways, traveling nearly flat along the plane of the planets. They told us about the wall at 2 points. They could never show us the whole shape from above. A newer NASA mission called IMAP launched in September of 2025 and now stationed out past the moon, began its science work early this year, mapping that boundary from the inside. But to see the real form of the bubble we live in, there is still only one way. Rise high above the plane and look down on all of it at once. To see our own home's true shape. A probe would have to do the single thing physics keeps forbidding, climb straight up. So how could it ever? How? You cannot solve this by building a bigger rocket. The fuel needed to erase 30 kilometers per second by brute force is beyond anything we can launch. So the way up turns out to run in the opposite direction from the one every instinct points to. Instead of aiming your engines at the sky and trying to climb, you do the reverse. You let the spacecraft fall, drop it inward toward the sun. Here is why that works. And it is one of the oldest tricks in spaceflight, written down by Hermann Oberth back in 1929. A rocket engine gives you far more energy when you fire it while already moving fast, deep inside a strong gravity well, than when you fire it out in empty space. Picture pushing a child on a swing. Shove at the very bottom of the arc when they are moving fastest, and they fly much higher than if you push anywhere else. A probe that falls toward the sun is doing the same thing, racing inward, picking up speed, until at its closest pass it is moving well over 100 kilometers per second. Studies suggest making that burn at only 3 to 6 solar radii from the surface, screaming through the bottom of the sun's gravity well. Fire the engine there at that one instant, and the dive becomes the launch pad. This is not just a thought experiment on a whiteboard. The technique sits at the heart of real proposals. The Interstellar Probe Study at the Johns Hopkins Applied Physics Laboratory and Project Lyra, drawn up to chase interstellar visitors like Oumuamua, with launch windows sketched for the early 2030s. The cheapest way to set up the dive is to fly out to Jupiter first and throw away almost all your sideways speed there. Exactly the kind of planetary slingshot Ulysses already used to reach the poles. Some have asked about using Uranus, whose axis lies nearly sideways. Clever, but it sits too far and too slow to help. A solar sail could do it too, the patient way, riding the faint push of sunlight with no fuel at all, slowly winding its orbit upward over years. So picture two missions on the table. One unfurls a solar sail and climbs above the pole slowly, patiently, on nothing but light. The other dives straight at the sun and rides one violent burn out of the plane. If you had to fund the first probe ever to climb above the sun, which would you bet on, the patient sail or the dangerous dive? Tell us below. Say we pull it off. A probe finally climbs above the plane. What would it see? The first thing it would do is rise out of the dust. Our flat sheet is hazy, filled with the crumbs of crumbling comets and ground-up asteroid dust, built up over billions of years. You can see that dust yourself on a dark night. A faint cone of light leaning up from the horizon after sunset. We call it the zodiacal light. The dirtiest seat in the house is the one we are stuck in. A telescope that climbed above the plane would leave most of that haze behind within months, into a view clean enough to hunt for the faint fingerprint of life around other stars. Up there, the wind changes too. The probe would sit in the fast polar stream Ulysses once tasted, near 750 kilometers per second, nearly double the slow, ragged wind down in the plane. And then it would turn its camera around and look back down. For the first time, a machine would see the whole solar system from above, spread out like a disk, the way no human ever has. Our most famous family portrait, the pale blue dot that Voyager 1 took in 1990, was still shot from inside the plane, looking sideways across the disk. The one looking down on our own home from above it has never been taken at all. The direction easiest to imagine is the one we understand the least. Not because it is far, but because a wall of speed has pinned us to a single flat sheet. Free to wander sideways forever, never once able to step off and look back. We have only just glimpsed the poles of our own star in a year most of us lived through. We still have never seen the true shape of the bubble we are breathing inside right now. Of every image we have ever lifted into the dark, of Mars and Saturn and Pluto, of dying stars and distant galaxies, the one looking down on our own house from outside is still missing. It is the closest photograph there is, and it is the only one we have never been able to take. If you want to keep looking out that strange direction, the icy shell, the other stars, the rest of the galaxy waiting above the sun's pole, that is where this story goes next.